Hi, and welcome back to Introduction to Deep Learning. In session 8 today, we're going to talk about transfer learning and autoencoders. So let's get started. So today, I quickly want to recap and have a few notes on hyperparameter tuning again. After that, we are going to have a look at exercise 8. And here, we're going to first look at batch normalization and dropout. These are like two additional techniques how to improve and also regularize the network. And then we are going to talk about transfer learning and autoencoders, which is the main part of the exercise. In the last part of the session, I quickly want to talk about basically how you can build up some kind of reputation or promote yourself to get some exposure with your coursework, with your projects, or basically projects you've done in your free time, and how you basically can promote these, which will be really helpful. For example, if you're gonna have internship interviews or actually like already interviews for jobs later on, basically how you can build up a small portfolio and what's important here and maybe other things which might not be that important for these kind of portfolios. But first, let's get back to hyperparameter tuning again. So you already saw how important it is to choose a good set of hyperparameters, but you also saw how many knots there are to tune and to turn basically, and it's quite experimental. So to some extent, there are basically shared knowledge about, okay, what to do in certain cases, but still there's a lot of trial and error, and also basically getting a sense of how these parameters will influence. And also what kinds of metrics, for example, to look at to see what's actually helping or which is not really helping. If you haven't checked out the slides on hyperparameter tuning, yeah, definitely check them out on Piazza. It's basically the solution to previous exercises. And it's a really good starting point to get a sense of, yeah, what's a good set of hyperparameters, at least in this case. Because like you will see, regardless of how many resources you have, if you're a company, you can maybe have like a huge compute cluster. If it's like a project you are going to do in your free time, you maybe only have like a CPU or like online resources like Colab. Yeah, regardless of your resources, it's really important to understand the set of hyperparameters that you actually can tune. Unfortunately, right now, there is no solution which is going to fit like every problem you're going to face. So basically, for every new project or problem we're going to train a neural network, you have to have a look at the hyperparameters again, tune them differently, and see how they influence the performance. In the two previous exercises, we were working on a really small data set. So here we could do like a quite decent grid search on few design decisions and parameters, because like the network was so small and the data was also rather small, so we can train our network within several minutes. But later on, if you have like a large data set and a large network, which is maybe going to train for several days or even weeks, this kind of grid search is not really possible anymore. So here it's basically important to understand how you efficiently can choose a hyperparameter set to converge to a good solution. And like here, there's one advice. If you think you need more practice, you can have a look again at the optional exercise from previous week on Cypher 10, because as I said here, it's a small data set and a rather small network, so this can be trained within several minutes. But it's a good starting point to understand what kind of design decisions and parameters there are and how these influences the performance. And with the previous exercise, this was implemented basically in PyTorch or PyTorch Lightning. And the nice thing is that this hyperparameter tuning is basically such a common task nowadays that there are already like some software solutions to automate this. For example, here's Optuna, and this can be integrated with PyTorch, for example, which does some search for you in an efficient way. So here there are already some solutions, but again, because it's an introductory course here, it's still important to understand what's happening under the hood. Okay, so now let's continue with other techniques, how we can improve the training even further. So in the lecture, we already heard about batch normalization, and I quickly want to recap this idea. And the thing with like deep networks is that the activations basically, even after a few layers, will die. So here in that example, in the upper row, you can see that at the very beginning of the network, the distribution of your activation or weights is still rather appropriate and like nicely distributed. But even after a few layers, these will deteriorate and basically be quite meaningless. The idea of batch normalization is to keep this kind of nice normal distribution throughout the layers, even for deeper networks. And as I said, the idea behind batch normalization is that you try to enforce like this zero mean and standard variation Gaussian distribution throughout the layers. And the idea here for batch normalization is that we can do so by normalizing the feature channels by the mean and variance within a single mini batch. So yeah, the idea behind is that we first try to normalize basically by the mean and the variance. And in the second step, we allow the network to change the range basically of the influences here. And in theory, the network could also learn to basically undo the normalization by basically learning the reverse of the normalization. Basically, if the normalization at the certain layer is not really helpful, the network can basically learn to undo those. And as part of this exercise, we have an optional notebook where you can implement batch normalization yourself and see how it works. The second approach you already heard of in the lecture is Dropout. So the idea behind Dropout is that we can reduce the capacity of our network, and that's helpful to regularize our network. For example, if we see the network overfitting, so the train error is way lower than the validation error. So the idea behind here is that with a certain percentage, we're going to drop out literally a certain amount of weights during the training. So a certain probability, we turn off the weights, and that basically reduces the capacity of the network and it forces the network to basically train with the remaining neurons. And similarly to batch norm for Dropout, there's also an optional part in the exercise where you can have a look at Dropout yourself and implement it in the notebook. All right, let's continue with the main part of this exercise. And here we first look at transfer learning, which is an important concept, which will also be covered later in the lecture, but we're gonna have it now here in this exercise. So what's the idea behind transfer learning? So let's take an example here. Basically, the problem statement here is that you want to build a classifier for cats, basically to say if this image shows a cat or not. The problem here is that you only have roughly 10,000 images, which might sound a lot, but in practice with like millions of parameters in your network is not that much. And you will see that either you will heavily overfit and also like that you won't generalize that well in reality. So again, the problem statement here is that as we know that deep neural networks need a lot of training data, but often it's either really expensive to collect this data or it's really just not possible. So for example, think for the simulation of car accidents, that here it's not really possible to collect like real data of car accidents. So one approach here, for example, to tackle this is transfer learning. And the idea here is that we try to learn on similar problems or tasks, which are, as I said, like closely related to the problems we are facing. And now what we basically want to do is that we want to transfer the knowledge which was trained in one neural network and try to transfer it to the task for another network. And yeah, this basically can be rephrased as trying to reuse at least parts of the network which was pre-trained for the new task. If you look at this at the more theoretical point of view, we can think of that we have like two different distributions. One is the source distribution, and the other one is the target distribution. And now we can think that for the source distribution, we have like a large data set. And in our case, the target distribution is rather small. And so what we basically want to do is that we want to use what has been learned like from the large data set and try to transfer it to the small data set. And basically reuse or map this distribution to the other distribution. The usual way how you would approach like training a new classifier would be that we have like some kind of data set and also our network. And in this case, like because we're working on images, one possible network architecture would be like a convolutional neural network. And the last part of the network is like the classifier, which can be implemented as a fully connected classifier or network. And basically you can think or basically split up this entire network into a feature extractor and a classifier. And here, because like we have like this binary setting between cat or no cat, we only have two different classes or two different possibilities. And when you approach this problem, you will have like an untrained network. And what you can do and what we have been doing so far was, okay, we just train the entire network with the data which we are given. And depending on how big the data set is, it might work or it will heavily overfit. And like all this entire network is basically the set of trainable parameters. What we can do instead is we can train on a really, really huge data set, for example, ImageNet. And here again, we have a feature extractor and our classifier. And ImageNet consists of 1,000 classes and millions of images. And here, we have basically this finely trained model. So what we would now want to try is basically, because like here in ImageNet, we have like such a huge variety that we can think of that the network was able to extract like usable features or reasonable features, which might transfer well to other tasks, because like in these 1,000 classes, there's most likely also the class for cat. So what we would do now is basically, we take this part, the feature extractor, which was pre-trained on ImageNet on these 1,000 classes, but only up to a certain layer in the network. And what's left is only like the classifier part, so the last few layers or the last layer even, which will then map to our new set of possible classes. So in our case, only the two classes. And you will see that basically this huge block of the network contains like most of the parameters. And for the network, it's like only a small part. So here, the chances of overfitting if we only would be training on this small part is like really small. There are a few possible different ideas how you can basically treat these different kind of pre-trained parameters or newly initialized parameters. For example, for the feature extractor, we could entirely freeze these parameters, which mean that during training, we don't optimize these weights at all. Other strategies would be, okay, for this particular part, we have a slower learning rate or also for the entire part, or we just treat it as, yeah, we don't do anything special. And yeah, as I said, the classifier is newly initialized. So here we need to train it. We need to train the weights as usual. So in this scenario, we were using, for example, ImageNet as pre-training for this feature extractor. However, there's also another possibility to be able to pre-train the feature extractor without having like such a large data set. And the idea is basically to use autoencoders, which is one possible way. And that's the second part of this exercise. But first, let's define what's actually an autoencoder. So the idea of an autoencoder is that we want to try to reconstruct the input. Like usually that sounds pretty trivial because we could just learn the identity function. The nice idea about an autoencoder now is basically that we try to compress the information by having like a lower dimensional bottleneck here in the middle. So let's take an example. If you have an image as input, which has a certain size of 100 by 100, for example, and the task is that we try to reconstruct it here in the output layer. However, here in the bottleneck, we, for example, only have like a vector of, let's say, 64 or 128 elements. And basically, the entire information to reconstruct the input need to pass through this bottleneck. So that's basically some kind of compression. And this entire concept here is then trained basically on images with an L1 or L2 loss on the raw pixels. So here basically the idea is that the network needs to find a good representation and a good way on how to compress what's in the input image to be able to still reconstruct like a plausible version as output. And the good thing here is that you don't need any labeling, like no categories or no segmentation or anything. The output should just be the input. And if you're, for example, familiar with the concept of PCA, you can think of something similar because like in PCA, we also want to basically distill the most important information. And in a sense, like here an autoencoder is trying to do the same by basically encoding the most essential information in this bottleneck. And yeah, what you also can do is basically you can define then or split up the network in two parts. One is the encoder part and the second one is the decoder part. And it also makes sense to also have this already set up like this in your network architecture, that you have two different subnetworks basically, one which is called encoder and one which is called decoder, because you already can think of the encoder as basically your feature extractor. So the encoder needs to extract useful features from the input such that the decoder can reconstruct a plausible version of the input. Now that we went through the definition of an autoencoder, let's see how we can use such an autoencoder for transfer learning. So the idea here is pretty straightforward. So as a first step, we train, for example, one of these autoencoders on a large unlabeled dataset. And this dataset could be quite similar to our target dataset, just without any labels. So now, after training this autoencoder on trying to reconstruct the input, we can go to the second step and basically taking the first part, the encoder part, which is now pre-trained, and use it as the feature extractor for our classification network. So that is basically the first part which we saw previously, the feature extractor. And from this part on, we can attach basically our classifier at the end. With this two-step process, you have seen how we can use an autoencoder for transfer learning. So the encoder basically encapsulates a good representation of features, which then should be useful for the classification task. And then basically as a third step, which we have seen before, is basically that you then can train your feature extractor together with your classifier on your target dataset. That's basically everything for exercise 8, and also which is again like a mandatory submission for the bonus. So I think, yeah, autoencoders are an important concept also for unsupervised learning. And also you can think of it as a compression algorithm in a sense to distill the main ideas and the main features of a data set. So in this last part of the session, I quickly want to, like off topic, talk about GitHub and exposure. So the first question here is maybe, why do I want to have exposure or like some kind of portfolio via GitHub or something like that? So the answer here is basically, assuming that most of you are like in your first, second, or third master semester, at some point you're going to face the question, okay, where I'm going to do internships or applying for jobs. And here, having already some kind of exposure or like a portfolio to showcase to recruiters or to be visible to recruiters is really helpful in the job market or also internally in the university. So what is helpful in this kind of process? So let's maybe think about the interview process when a recruiter interviews you for an internship or a job. And basically everything is important here where you can talk about and show that you've done like some nice work. What's maybe not that helpful is if you would just post or dump your solutions from these exercises here from I2DL on, let's say, GitHub, for example. First of all, recruiters will not really be impressed by you just dumping the structure of the entire exercises on GitHub. And secondly, it's also not really helpful for other students because we designed these exercises in such a way that basically you gain hand-on experience by doing so and not like only for the bonus. So yeah, here I want to also mention that we still have the copyrights on the exercises themselves. So please don't just post the entire solution and the entire structure on GitHub. But maybe on the bright side, let's talk about like what's really cool for recruiters and for yourself. So these are actually basically projects themselves. So here you can think of any kind of cool projects you did in internships, in guided research here at the university, or also like any cool projects you did in your free time. And here it really helps to document the process, like your thought process, how you approach the problem, what was the actual task, the task definition. And here you can really play around like to have like a really nice repository on GitHub, or even have like a project page with these GitHub IO pages. And here, yeah, you can really showcase what you've done. And that's way more important for recruiters. And with these, you can really stand out. And yeah, here are like some small notes, what you can actually highlight in these projects. So as I said, you should like just really document what you have done, what problems did you face, how you approach these problems. Then also like here in Introduction to Deep Learning or generally Deep Learning, you should visualize the data. What's the input data? Can you already have any assumptions or prior knowledge about the data and the data pre-processing? And also like discuss your design decisions. As you saw, there are so many design decisions and how did you, for example, choose the hyperparameters. And what's also really cool is if you then publish this kind of code, like not these ready-made I2DL exercise solutions, but the code which you developed yourself. And like with these kinds of project pages, are really nice polished GitHub repositories, you can really stand out for internships, for jobs later on, or also like to get into any of the research labs here at the university. And I hope this kind of off-topic note helped you to motivate you to think about these kinds of projects, how you can use them to stand out during the recruitment process, and just generally motivated you to think about also the future and how you can use like free tools such as Github to promote yourself. So let's quickly summarize. So next week on Monday, you should watch lecture 9 about convolutional neural networks, which you probably already heard of, but there you will learn a lot more about. And yeah, then there will also be the exercise submission for exercise 8, which, as we just introduced, is about like transfer learning and autoencoders. So the submission deadline here is on June 9, yeah, at the usual time. And the next tutorial will be on the day after, so June 10, and this will be about facial key point detection. So thanks for listening and see you next week.